Welcome to the Sleepy Scholar. It's lovely to have you here tonight. Wherever you are right now, settle in. Maybe you're under a blanket with just one lamp still glowing in the corner. Maybe you're on a train or a couch or lying flat with your eyes already half closed. However you've arrived, I'm glad you came. And before we begin, I'm curious. Where in the world are you watching from tonight? What time is it in your corner of the world? Leave a little note if you feel like it. I love reading where these quiet evenings reach. And if you enjoy these slow journeys and want more of them, a gentle like and subscribe really helps this sleepy little channel keep going. Small creators like me genuinely rely on it. It's the quietest kind of support, and it means more than you'd think. To those of you already subscribed who keep coming back night after night, thank you. Truly. You're the reason the lamp stays on. Now, I'll make you the usual promise. We're going to move slowly tonight, very slowly. There's nothing here you need to grasp, nothing you have to hold on to, no test at the end of the hour. If you drift off somewhere in the middle, that's perfectly fine. The ideas will still be here when you wake, and so will I. I'll try not to make tonight so interesting that it keeps you up. Though if it does, well, at least you'll have learned something lovely about the sky. A fair trade, I think. So let your shoulders drop. Let the day go. And let me tell you something strange and true about exactly where you are. Right now, as you lie there, breathing slowly in the dark, you are sitting inside a hole. Not a hole in the ground, not a hole in the wall, a hole in space itself. An enormous hollowed-out cavity in the fabric of the galaxy, and you, your bed, your house, your whole planet, the sun, every other planet circling it. All of it sits tucked inside this hole. We have a name for it. We call it the local bubble, sometimes the local cavity. And it is the place we live, the neighborhood, the room we're all in together, you and I and everything else nearby. And here is the part that's hard to even picture, so let's not rush it. This hole is roughly 1,000 light years across. Let that sit for a moment. 1,000 light years. I want to give you a sense of what that really means, because a number that big can just slide right past you in the dark, and I don't want it to. I want you to feel it. Light is the fastest thing there is. Nothing in the whole universe moves quicker. The light from your lamp reaches your eyes in less than the blink of a blink. Instantly, as far as you'd ever notice, light could circle the entire Earth more than 7 times in a single second. It's a runner that never slows, never tires, never stops, that fast. And to cross from one side of our bubble to the other, that tireless runner, that beam of light moving at the absolute speed limit of everything, would need 1,000 years. Think about that. If a flash of light left one wall of our cavity at the moment some medieval scribe was dipping a quill into ink, copying out a book by candlelight, it would still be traveling now. It would still have a little way to go. 1,000 years of human history, kingdoms rising and falling, languages being born and forgotten, your great-great-great-grandparents and theirs stretching back further than any family memory. And in all that time, light would only just be making its way across the empty room we live in. That is the true scale of the bubble we live in, not a tidy little pocket, not a cozy local circle, a void so wide that the fastest thing in existence takes 10 centuries to cross it. And we, this entire solar system, the sun and all its planets, we sit somewhere near the middle of it, a tiny, warm, lit-up speck floating in the center of 1,000 light-year hollow. Hold that picture gently as we go. You right now in the middle of an enormous emptiness, breathing slowly, perfectly safe. Because here's the thing about this hole, it isn't just big, it's empty in a way that's almost impossible to imagine. And I'd like to take some time with that emptiness because I think it's beautiful once you sit with it. When we say empty space, most of us picture truly nothing, a perfect, clean vacuum. But real space, ordinary space out there between the stars, is never quite nothing. There's a thin haze that fills the gaps. Astronomers call it the interstellar medium. That's just a fancy name for the faint scattering of gas and dust drifting in the spaces between the stars. Mostly hydrogen, the lightest, simplest stuff there is, so thin you'd never feel it, so sparse it's barely there at all. But it is there. A whisper of substance filling the dark. In a typical stretch of that interstellar medium, that thin haze between the stars, you'd find something like half an atom in every cubic centimeter of space. Let me make that real for you. A cubic centimeter is about the size of a sugar cube. That's small. So out in ordinary space between the stars, take a little sugar cube-sized box of nothing, and on average you'll catch about half of one single atom inside it. Half an atom. In a box you could balance on your fingertip. Compare that to the air you're breathing right now, the air filling your room as you lie there. That same sugar cube box here on Earth holds something like 25 billion atoms. Billions of billions packed together so densely we feel it as solid, breathable air. And out in the space between the stars, half of one atom in the same little box. Well, that's how thin ordinary space already is. That's what we call full out there. Now, here's where our hole gets strange. Inside the local bubble, inside our cavity, the place we actually live, it's even emptier than that. Far emptier. The density inside our bubble drops to something like 5/100ths of an atom per cubic centimeter. 5/100ths, which is roughly 1/10 of even that already ghostly interstellar haze. So take that sugar cube box again, the one that out in normal space might hold half an atom, bring it inside our bubble, here where we live, and on average you'd have to wait. You'd have to gather up 20 of those little boxes just to find a single atom hiding in one of them. Our home is 10 times emptier than the already nearly empty space around it. We don't just live in a void, we live in a void hollowed out inside the void, a clearing in the thin forest, a quiet pocket inside the quiet. And to really feel just how empty that is, let's go the other direction for a moment. Out there in the galaxy, scattered around, there are places that are dense, by space's standards anyway. We call them molecular clouds. Great cold drifts of gas and dust where new stars are slowly being born. And in those dense clouds the count climbs to hundreds, sometimes thousands of atoms in that same little sugar cube box. Thousands. So picture the range. A rich molecular cloud, thousands of atoms per box. Ordinary space between the stars, half an atom. And our bubble, our home, 5/100ths. A tenth of a tenth of a tenth of even those clouds. We live in one of the emptiest neighborhoods in this whole corner of the galaxy. A grand, hushed, hollowed-out hall with the lights of the sun glowing softly in the middle of it. I find something deeply restful in that, honestly. We tend to think of space as crowded and chaotic, full of danger and noise, but the truth of where we actually sit is the opposite. We live inside an enormous, gentle quiet, a clearing. There's almost nothing around us for a very, very long way. Just a thin, soft emptiness and the slow, patient drift of the stars. You can picture it like a great dark cathedral, vast and still, with you resting somewhere near the very center of the nave, and the ceiling so far away the light from it takes 1,000 years to reach the walls. But now, and I told you we'd move slowly, so let's just ease into this. Now a question should be tugging at you, a small thread to pull on as you drift. If this place is so empty, if it's a hole, a void, a near-perfect nothing, then how on earth do we even know it's there? Think about that for a second. How do you map a thing that is, by its very definition, almost nothing. How do you draw the walls of an empty room when the room is made of emptiness? You can photograph a star, sure. A star is bright, it shines, it announces itself. You can photograph a glowing cloud of gas lit up by nearby suns. Those things give themselves away, but a hole, an absence, a region defined entirely by what isn't there, it would be a little like trying to take a photograph of a quiet, or to draw the exact shape of a silence in a room. How would you even begin? And yet somehow we have done it. Astronomers have mapped this bubble, measured its width, traced its edges, even worked out its strange, lopsided shape. They know roughly how empty it is, and how hot the little wisp of gas inside it runs, and where its walls press up against the denser clouds beyond. They've drawn the silence. They've photographed the quiet. We'll get to exactly how they pulled off that quiet little miracle a bit later tonight. And the answer is genuinely lovely. It involves a faint, ghostly glow and a clever map built grain by grain out of starlight and dust. But for now, just hold the wonder of the question itself. We can see a hole. We have measured a place that is almost entirely nothing at all. Keep that little thread in your hand as you drift. We'll follow it. For now, let's stay with the shape of the place, because if you're picturing our bubble as a neat, round ball, a tidy little marble of emptiness with the sun sitting at its perfect center, I want to gently set that picture aside. The truth is stranger and softer around the edges, and I think more beautiful. Our cavity isn't a sphere. It isn't tidy at all. When astronomers finally mapped it in 3 dimensions, when they built up a real model of its shape, not just a flat circle on a chart, but a thing you could turn over in your hands and look at from every side, what they found was lumpy, irregular, squashed and stretched in places, bulging in others. Some people describe it as peanut-shaped. Others say it looks more like a chimney. A great crooked cavity, wider in some directions than others, with the sun riding along somewhere near the middle of the wide part. A chimney. I love that word for it, because of what it suggests. A chimney is open at the top. And our bubble, it turns out, isn't sealed shut on every side like a soap bubble would be. It seems to open upward, out of the flat plane of the galaxy, the crowded disk where most of the stars and gas live, and up toward the thinner, emptier reaches above. The galactic halo, we call that upper region. The vast, sparse outskirts that wrap around the bright disk of the Milky Way like a faint glow around a city seen from far away. So picture it now, slowly, with me. Not a marble, not a perfect ball, a great, irregular, hollow, peanut-shaped, chimney-shaped, lopsided and crooked, with one end opening up and out toward the quiet halo above the galaxy's bustling plain. And somewhere down in the wide belly of it, a single ordinary yellow star, our sun, drifting along with its little family of planets. One of which is yours. The one you're lying on right now. The people who first pieced this shape together, who built that 3-dimensional map of our hollow home, were a team of astronomers, led in large part by a researcher named Catherine Zucker, working alongside colleagues like Alyssa Goodman and João Alves. In a study published in the journal Nature back in January of 2022, they did something that, when you sit with it, is quietly astonishing. They reconstructed the 3-dimensional shape of the bubble, and not just its shape as it is now, but something of its history, the story of how it came to be hollow in the first place. We'll come to that story, the carving of it, in time. It's the heart of tonight. But for now, I just want you to hold their gift to us. A real map of the empty room we live in. A picture of the shape of our local quiet. And the way they built it is itself worth resting on for a moment, because it's so patient, so painstaking. They didn't measure the emptiness directly. You can't. Not really. Instead, much of this kind of work leans on tracing the dust, the faint grains of dust scattered through space between the stars. Other astronomers, in careful surveys, work associated with names like Lallemant and colleagues, mapping the dust in 3 dimensions, had been building up, star by star, a picture of where the dust thickens and where it thins. And here's the clever part. Where there's no dust, there's the hole. The emptiness shows itself not by what it contains, but by the absence. The gap, the clearing, the place where the dust simply isn't. They mapped the walls by mapping where the walls stop. They found the silence by listening for where the sound goes quiet. It's the same trick, in a way, as finding a clearing in a dark forest by walking until the trees thin out. You don't see the clearing directly in the night, but you feel the openness. You sense the edges where the dense wood gives way to open sky. And grain by grain, star by star, measurement by patient measurement, astronomers walked the edges of our clearing until they had its whole crooked shape laid out. A peanut, a chimney, a hollow 1,000 light years wide, open at the top toward the halo, with us drifting in the middle. I want you to stay with that image as your breathing slows. You in your bed, in your room, on your planet, circling your star, and your star drifting through the wide belly of an enormous, crooked, gentle hole in space, a clearing in the forest of the galaxy, 10 times emptier than the already empty dark around it, so vast that light takes 1,000 years to cross it, and so quiet. There's nothing pressing in on us, nothing crowding close. For a very, very long way in every direction, there's almost nothing at all. Just the thin, soft drift of a few stray atoms far too sparse to ever feel, and the patient glow of distant stars on the far walls. We are, in the most literal sense, living in a wide-open, hollowed-out hush, a hole in space, a pocket of deep quiet, with the lamp of the sun lit gently at its heart. And yet, and here's the next little thread for you to carry into your dreams. A hole like this doesn't simply happen. Empty rooms don't hollow themselves. Something cleared this space. Something dug this enormous cavity out of the thin haze of the galaxy and pushed all that gas and dust away to the edges where it now waits piled up against the distant walls. A void this big, this clean, this deliberate looking, even though, as we'll see, nothing about it was deliberate at all. A void like this has a cause. Someone or something did the digging. And the diggers, it turns out, were stars. Stars that lived and burned and died long, long before you or I or any human being existed to look up and wonder about them. Stars that ended their lives in the most violent way the universe knows how, and in dying, in their last enormous breath, blew this very hole that now shelters us. The walls we live inside were carved by the deaths of suns, but that's the story for a little later. For now, just rest in the strangeness of where you are. 1,000 light-year hole, 10 times emptier than empty, peanut-shaped and chimney-topped and open to the halo above. Mapped by the absence of dust, by the place where the trees thin out, and you somewhere near the warm middle of it, breathing slow, perfectly safe, drifting. Let your eyes close if they want to. We've only just begun, and there's no rush at all. The hole isn't going anywhere. It's been here for millions of years, and it'll cradle us gently for millions more. So, settle deeper. Let the number, 1,000 light years, soften into a feeling rather than a fact. A vast, kind, hollow quiet all around you, holding you, while the sun keeps its slow, lamplit drift through the middle of the dark. And as you settle, hold those two little questions loosely like threads laid across your palm. How do you measure a thing that is almost nothing? And what kind of force could possibly carve a hole 1,000 light years wide? We'll follow both of them slowly, gently into the quiet. There's a glow to find, faint and 1,000,000 degrees hot. And there are the diggers themselves to meet. The stars that died to make us this home, but not yet. For now, just breathe. Just rest in the wide, soft emptiness of the place you live. You're in the middle of an enormous, ancient, gentle hole in space, and nothing is closer to you than the slow drift of a few stray atoms and the patient light of distant suns. There is so much room here, so much quiet, so much space to simply rest, and we have all the time in the world. Welcome to the Sleepy Scholar. It's lovely to have you here in the warm middle of all that emptiness, wherever you happen to be tonight. And I do mean wherever, because I'm always a little curious. Where in the world are you watching from? A bed somewhere, I'd guess, the lamp still on, the blanket pulled up. Or a couch, a chair, a train carriage rocking gently through the dark. Maybe a long drive home, the road unspooling ahead. Tell me, if you feel like it, down in the comments, where you are and what time it is in your corner of the night. I love reading them. It makes this little hole in space feel a touch less lonely. And if you enjoy these slow journeys, if you'd like more nights like this one, a quiet like and a subscribe really does help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. So thank you truly to everyone already here. You're the reason there's a next one. Now, settle back in, because I made you a promise, and I mean to keep it slowly. There's no test at the end of this, no need to follow every thread. If you drift off somewhere in the middle, that's not a failure, but that's the whole point. The ideas will still be here when you wake. The hole in space will still be 1,000 light years wide. I'll just keep talking, soft and low, and you can let the words wash over you like water over smooth stones. We'll take it slow tonight, slower than slow, one small wonder at a time, with long pauses to breathe between them. So let me give you something to rest your mind on, something to make that number, 1,000 light years, stop being a number and start being a feeling. You're inside the local bubble, that's the name astronomers give it, the local cavity sometimes, a region of space scooped almost clean, and you live near the center of it. Now you might think of empty space as already, well, empty, nothing out there, the void between the stars. But space is never quite empty. There's always something, a thin haze of gas and dust drifting between the suns, so faint you'd never notice it. But there. Astronomers call it the interstellar medium, the stuff between the stars. A whisper of hydrogen, a breath of dust spread impossibly thin across the dark. And in ordinary interstellar space are the normal kind, the average kind. That whisper amounts to something like half an atom in every cubic centimeter. Picture a sugar cube, a little cube of space the size of a sugar cube sitting in front of you. In ordinary space, that little cube would hold about half an atom. Half. Not even a whole one. That's how thin the haze between stars already is. And yet, inside the bubble where you live, it's far thinner still. Inside our hole, that same little sugar cube of space holds, on average, about 5/100ths of an atom. 0.05. 10 times emptier than ordinary empty space. 10 sugar cubes lined up in a row, and somewhere across all 10 of them, you might find a single, lonely atom drifting. And that's the air, if you can even call it that, of the place we live. Let that settle for a moment, because we throw the word empty around so easily. But this is a different order of empty. This is empty made deliberate, empty scooped out and swept clean. And to feel just how clean, you have to know what the full places look like, the crowded corners of the galaxy. Out there, in the great cold nurseries where stars are born, the gas and dust gather thick. Molecular clouds, they're called. Vast dark folds of material, collapsing slowly under their own weight into new suns. And in a molecular cloud, that same little sugar cube of space might hold hundreds of atoms, sometimes thousands, where our bubble holds 5/100ths. The contrast is almost too large to picture. If our whole is a held breath, a molecular cloud is a thick, wet fog you could lose your hand in. And we live in the breath, the clear, quiet, hollow breath. So here you are, floating near the middle of a cavity 1,000 light years across, 10 times more empty than the already unimaginable emptiness around it. Hundreds, thousands of times emptier than the dense clouds where stars are made. You are about as alone, in the simplest material sense, as it is possible to be inside a galaxy. And somehow, that isn't frightening. Somehow, it's the most peaceful thing in the world. All that room, all that quiet. No crowding, no noise, just the slow drift of a few stray atoms and you breathing in the middle of it. But here's where it gets a little strange. And this is the first of those threads I asked you to hold loosely across your palm. If the bubble is almost nothing, if it's 10 times emptier than empty, then how on earth do we know it's there at all? Think about that for a moment slowly. You can't see emptiness, you can't photograph a hole. Point a telescope at the place where the local bubble is and you're pointing it at more or less nothing. No glowing cloud to catch the eye, no bright wall to mark the edge, just dark, and a little darker, and the distant stars shining through from far beyond. How do you measure a thing whose entire defining quality is that it isn't there? It's a lovely sort of puzzle, isn't it? The kind that sounds impossible right up until someone finds the clever way around it. And there are clever ways. More than one. We'll get to the faint, hot glow of it. That whisper of 1,000,000-degree heat I promised you. The lingering warmth that gives the secret away. But the first way, the gentlest way, the way that gave us the most beautiful map, is to stop looking for the bubble itself, and to look instead for its walls. Because here's the thing, the dust I mention, that fine, faint haze drifting through interstellar space, it does one very useful thing for us. It blocks light. Dust dims and reddens the stars behind it, the way wood smoke dims a street lamp, the way haze softens a distant hill. So even though you can't see empty space, you can see where the dust is and where it isn't. You can map the haze by watching how it blots and reddens the starlight passing through it. And in 2022, a team of astronomers did exactly that. Catherine Zucker, Alyssa Goodman, João Alves and their colleagues, working with measurements from across the sky. They built a 3-dimensional map of all that nearby dust. Not a flat picture, but a true model with depth, where they could fly a viewpoint through the local neighborhood of the galaxy and see in the round where the dust gathered thick and where it thinned away to nothing. And what they found when they looked at the shape of the thinning was the bubble. Not by seeing it, by seeing the hole it left in everything else. The place where the dust simply ran out. A great clear cavity with the gathered dust and gas pressed into a shell all around its edge, like the inside of a soap bubble where the soap collects at the surface and the middle is just air. Mapped by absence, measured by the place where the trees thin out and the clearing begins. Isn't that a quietly wonderful idea? You find the nothing by carefully drawing the shape of the something around it. You trace the silence by mapping where the noise stops. And the shape they drew was not the tidy thing the textbook diagrams always promise. We say bubble, and your mind reaches for a perfect sphere, a smooth, round ball of cleared space with us sitting neatly at its heart. But reality is rarely so neat, and the real local bubble certainly isn't. It's lopsided, lumpy, stretched longer one way than another. The astronomers describe it as peanut-shaped or sometimes chimney-shaped, and both of those are better pictures than a ball. A peanut with its two rounded lobes pinched in the middle, a chimney with an open top. Because that's the other surprise, the bubble isn't sealed. It isn't a closed pocket of clean space tucked snug inside the galaxy. It's open at the top, open upward, out of the flat, crowded disk of the Milky Way where all the stars and gas and dust are gathered, open toward the thin, quiet halo of the galaxy above and beyond. As though something carved this hole and then kept pushing, kept venting upward until the cavity broke through the ceiling of the galactic disk and let its hot, thin breath escape into the great open space overhead. A chimney, a flue, a hole that doesn't just sit there, but draws upward, out of the smoke and into the clear. So adjust the picture in your mind gently before you drift any further. Not a ball. A great irregular peanut of cleared space, longer than it is wide, lumpy at the edges with a chimney open at the top, venting up into the halo. And you drifting somewhere near the warm middle of the long axis, near the pinch of the peanut, breathing slow. It took light 1,000 years to cross the long way, across your empty room. 1,000 years ago, on the far wall, the light set out. And it's only reaching the near wall now. That's the size of the place you live. That's the scale of the quiet around you. And we still haven't met the thing that made it. We've only mapped the shape of the wound. We haven't yet found the blade, because a hole this size, this clean, this open-topped, it didn't simply happen. Something carved it. Something swept all that gas and dust outward and pressed it into the shell where the new stars are quietly being born, even now. Something poured energy into this corner of the galaxy, enough to scoop out a clearing 1,000 light-years wide and to leave the leftover gas glowing at a temperature you wouldn't believe. That's the second thread, the one still resting across your palm. What kind of force carves a hole this big? But not tonight's worry. Not this breath. For now, you have the shape of it, and the emptiness of it, and the quiet way we found it, by mapping the dust and finding the clearing. That's enough to rest on. A peanut-shaped, chimney-topped hollow in the dark, 10 times emptier than empty, traced by the absence of dust, holding you softly near its center while the stars shine patiently through from far beyond the walls. So let your shoulders sink a little further. Let the map fade into a feeling again. You don't have to hold the shape in your mind. Let me hold it for you. You just rest. There's a glow to find, faint and ancient and impossibly hot, waiting on the other side of this quiet. And there are the diggers themselves still to meet, the ones who carved the clearing long before the first of your ancestors ever looked up. So let's talk about that glow, because here is the thing about empty space, truly empty space, the kind we've been describing, 10 times emptier than the ordinary nothing between stars. It should be dark, it should be cold. If there's almost nothing there, there's almost nothing to radiate heat, almost nothing to absorb and re-emit energy as light. You'd expect a cavity 1,000 light-years wide, scraped clean of nearly all its gas, to be a kind of ultimate darkness, a silence so complete it doesn't even shimmer. And yet, when scientists began surveying the sky in soft X-rays, a band of radiation your eyes can't see, the kind that comes from extremely hot gas, they found something they didn't quite expect. The background glow wasn't coming from distant galaxies or from discrete point sources like individual stars. It was coming from everywhere at once, a soft, diffuse, all-sky whisper of X-ray light that seemed to fill the space around us like a fog. That is not what empty, cold, dark space does. The instrument that mapped this most carefully was Rosat, the Röntgen satellite, named after Wilhelm Röntgen, the physicist who discovered X-rays in the first place. Rosat surveyed the whole sky in the 1990s and returned a picture that glowed, not brightly, not like a fire or a beacon, more like the faint warmth you might see if you pressed a thermal camera against a warm stone in the dark. But it was there, all around us, a soft X-ray background that wrapped the solar system like a cocoon made of invisible light. The most natural explanation was also the most extraordinary one. The gas inside the local bubble, what little of it remains after all that sweeping and clearing, is not cool. It is not even warm in any sense we would recognize. It is hot, ferociously, absurdly hot, on the order of around 1,000,000 degrees Kelvin, 1,000,000 degrees. To give you a sense of how untethered that number is from ordinary experience, the surface of the Sun runs at roughly 5,700 degrees Kelvin. 1,000,000 degrees is nearly 200 times hotter than the face of the star that lights our days. The interior of our Sun, far down in its fusing core, reaches about 15 million Kelvin. But its surface, the part that gives us sunlight, the part that would instantly vaporize anything we know, is a mere fraction of what the gas inside the local bubble runs at. We are embedded in a region of space where the sparse remaining gas is hundreds of times hotter than the Sun's own face. Just let that sit for a breath. Don't try to feel it. You can't, and that's part of the wonder. This heat is not the kind that burns skin or warms a room. At these temperatures, atoms lose their electrons entirely, becoming bare nuclei flying through space. The gas becomes what physicists call a plasma, and that plasma, moving at incredible speeds, emits X-rays the way a hot iron emits infrared warmth. Not from fire, not from light, but simply from being as hot as it is. Rosat picked up that signature, and the signature whispered, "Whatever is in here has been heated to extraordinary temperatures, and whatever heated it must have been extraordinary." The word for something that heats gas to 1,000,000 degrees across 1,000 light years is not gentle, it's not gradual, it's explosive. But here is where it gets a little more nuanced, and where the story of measurement and discovery is itself worth a moment's attention, because science is always more honest and more interesting than a clean headline. After Rosat, as instruments improved, as sounding rockets carried detectors briefly above the atmosphere, and gathered more precise readings, researchers began to realize that the soft X-ray background is not entirely what they thought. Some of the glow, possibly a meaningful fraction of it, wasn't coming from the far reaches of the local bubble at all. It was coming from much closer, from right here, inside our own solar system. The process responsible for this is called solar wind charge exchange. Here's what that means in plain terms. The Sun breathes constantly, steadily, in a stream of charged particles called the solar wind. Those particles flow outward in all directions, filling the solar system with a thin cloud of ions moving at several hundred kilometers per second. Now, trailing through the solar system alongside us is a thin smattering of neutral atoms, gas drifting in from the interstellar medium around us. When a fast ion from the solar wind collides with a slow, neutral atom from that background gas, something specific happens. The solar wind particle captures an electron from the neutral atom, and in that exchange, the newly captured electron drops to a lower energy state and releases a photon, a soft X-ray photon, right here, close to us, not 1,000 light years away. This is solar wind charge exchange, and it turns out to produce soft X-rays in exactly the energy range that Rosat was detecting. which means some of what Rosat was seeing as a distant, bubble-filling glow was actually local noise, so to speak, X-ray emission generated within the solar system itself, not deep inside the cavity of the local bubble. What does this mean for the local bubble? The bubble is still real, the cavity is still there, still mapped, still glowing, but the picture is a little more complicated, a little more layered. The local bubble almost certainly does contain hot plasma at extraordinary temperatures. The supernova-heated gas is real, and the physics demands it. But the exact temperature, the precise brightness of the bubble's own interior glow, was partially mixed with this foreground signal that earlier measurements couldn't separate out. The DXL-sounding rocket mission, flown in the 2010s, was one of the instruments that began to untangle the two contributions. The honest picture, then, is this. The local bubble's interior is genuinely hot, genuinely radiating. But our early measurements slightly overstated how bright the bubble itself was, because some of what we were seeing came from our own doorstep. The refinement doesn't change the bubble's existence or its nature. It changes the precision of our temperature map. And science doing that, catching its own earlier error, correcting the picture without drama, quietly getting closer to the truth, is not a failure. It's the whole point. So there is a glow in here, ancient and real and genuinely extraordinary. Million-degree plasma, the lingering thermal echo of catastrophic events detectable across 1,000 light-years of emptiness by a satellite named after the man who discovered X-rays. You live inside that glow right now, though you can't feel it. The plasma is too thin to touch you, but the light it emits, the soft X-rays washing over the solar system from every direction, is the bubble announcing itself even in its emptiness. Now, we measured the glow. That told us there was something hot, something explosive in the recent history of this region. But measuring a glow tells you the temperature of gas. It doesn't tell you the shape of the cavity that holds it. And for the three-dimensional picture of where the walls actually are, where the boundary sits between the empty bubble and the denser interstellar medium beyond, for that you need a different kind of map. You need to map where the dust isn't. This is the elegant reversal at the heart of how we know the local bubble exists at all. You cannot take a photograph of nothing. You cannot point a telescope at an absence and get a picture back. What you can do is look at starlight, light from thousands and thousands of stars at different distances in every direction, and watch for reddening. When starlight travels through gas and dust, it gets dimmed and reddened, the way the sun looks orange near the horizon because its light is passing through more atmosphere. The more dust a star's light passes through, the more it's reddened. By measuring how much reddening each star's light has suffered, and knowing how far away each star is, you can reconstruct a three-dimensional map of where the dust is concentrated, and therefore where it isn't. This is what Lallement and colleagues were doing with three-dimensional dust extinction maps, and it's what Catherine Zucker, Alyssa Goodman, João Alves, and their team brought to its most complete form in their 2022 paper published in Nature in January of that year. Their reconstruction was not just a brightness map, not just a two-dimensional picture of where things glowed or darkened. It was a three-dimensional model of the cavity and its surroundings, built from the reddening of thousands of individual stars spread across a volume of space more than 1,000 light-years across. It was, in a real sense, a geographic survey, a topographic map, but in 3 dimensions, of a landscape made of gas and dust and the absence of both. And what that map showed was startling in the most beautiful way. The interior of the local bubble, the empty space, the low-density cavity, the region of hot, thin plasma you now know we inhabit, is clear of dense gas and dust. That's expected, that's the bubble. But the boundary, the shell, the swept-up wall where all that expelled material has piled up over millions of years. That wall is not empty at all. The wall is where the clouds are. Every single one of the major molecular clouds near the Sun, the dense, cold, dusty regions where new stars form, sits on the surface of the local bubble, not inside it, not scattered randomly through space, on the shell, like barnacles on the outside of a vast, slow ship. The clouds have names. Taurus, the cloud that has been forming stars in a leisurely, prolific way for millions of years, sits on the shell of the local bubble. Ophiuchus, one of the closest star-forming regions to Earth, sits on the shell. Lupus, Chamaeleon, Corona Australis. Each of these named clouds, each of them a nursery of new stars, each of them an object that astronomers have been studying for generations. Each of them sits right there on the surface of the expanding bubble, caught in the compressed sweep of expelled material. The Muska cloud, the Pisces cloud, on the shell. This is not a coincidence of numbers. This is not a statistical fluke. This is cause and effect. The supernovae that blew the local bubble didn't just clear the interior. They swept material outward in a long, slow, pressurized wave, and where that wave compressed the surrounding interstellar medium, it made the gas dense enough, cold enough, self-gravitating enough to begin forming stars. The local bubble's expansion caused the compression that triggered the star formation. The cavity created the conditions for the clouds on its walls, and the clouds on its walls are creating the next generation of stars. Think about that for a moment. The stars we see forming in Taurus right now, close enough that astronomers can watch individual protostars coalescing from gas and dust close enough to study in rich detail, are forming because a series of ancient supernovae cleared and compressed the medium around us millions of years ago. The destruction came first. The construction followed in the pressure wave of the destruction's aftermath. Violence, immense and long past, is the reason those stars are being born in those places at this moment. And the bubble is still growing. That shell is still moving outward, even now, at around 6.7 kilometers per second. This is not a fast pace in human terms. 6.7 kilometers per second sounds dramatic, but compared to the speed of the original supernova shockwaves which raced outward at thousands of kilometers per second in their first moments, this is the long, slow coast of a process that has shed most of its energy and is now gently drifting on momentum, but still moving, still compressing. New stars forming on the walls of a cavity, still quietly inflating from explosions that ended millions of years before humanity existed. There's something almost impossible to hold in the mind in the right way about that image. You are inside a structure that is still in motion from events that occurred roughly 14 million years ago. The echo hasn't finished echoing. The wave hasn't stopped waving. The universe here is still responding to events you cannot find in any human history because they predate your entire lineage, your entire genus, your entire order on the tree of life. And yet the motion continues quiet and steady at 6.7 kilometers per second. Let that settle. Now there is one more piece of this part of the picture, and it may be the most counterintuitive thing we've said yet tonight. We've established that we live inside the local bubble. We've established that the bubble is hot and glowing and empty and still expanding. We've established that every nearby star, nursery, clusters on its shell. And all of that might tempt you to imagine that this bubble was built around us somehow. That the sun sits at the center because the sun has always been at the center. That this is our cavity, our clearing, our cosmic home, carved by some process related to us and our star. It wasn't. The sun did not make this bubble. The sun did not cause these supernovae. The sun played no role whatsoever in the creation of the local bubble. The sun is not even an old resident It wandered in from elsewhere only around 5 million years ago, and it sits near the center of the cavity today for reasons that have nothing to do with the explosions 5 million years ago. To put that in perspective, the oldest members of the genus Homo, our earliest human ancestors, appeared on Earth somewhere around 2 to 3 million years ago. The Sun entered the local bubble before our own genus existed, and the bubble itself, the processes that created it, began roughly 14 million years ago, long before any hominin walked the Earth, long before the great apes took the shapes we'd recognize, long before much of the modern fauna of Earth had its current form. The local bubble is ancient far beyond the human scale. The Sun entered it relatively recently, and the Sun's position near the center of the cavity is a coincidence of timing and trajectory, not a sign of anything special or purposeful. This is, if you sit with it, actually one of the more quietly remarkable things about the local bubble. In the universe, there are events that feel like they were arranged for our benefit. The Sun is the right distance from Earth for liquid water. The Moon is the right size to stabilize Earth's axial tilt. These things feel, in a loose way, convenient. But the local bubble emphatically does not work that way. The supernovae that carved it weren't aimed at us. They weren't preparing a home. They were massive stars dying in ways that massive stars die, driven by nothing more and nothing less than physics. And the Sun, tracing its own path around the center of the Milky Way, wandered through the interstellar medium, crossing into the expanding shell of the bubble around 5 million years ago and drifting inward, carried by its own orbital motion, until it ended up somewhere near the center. A coincidence that will eventually reverse itself as the Sun continues moving and the bubble continues expanding until the geometry shifts and we are no longer quite where we are tonight. The Sun is a tourist. The local bubble is someone else's explosion. We are borrowing the silence, and inside that silence, inside the already vast bubble, there is one more layer of structure worth knowing about, because it is the part we inhabit most immediately, the innermost Russian doll in a set you didn't know you were nested inside. Within the local bubble, which is itself roughly 1,000 light-years across, the Sun is currently passing through a much smaller region, a little wisp of warmer, denser gas, still far emptier than anything on Earth, but measurably different from the thin, hot plasma of the bubble's main interior. This wisp is called the local interstellar cloud. It has a nickname, which you may find either charming or absurd, depending on your disposition. The local fluff. It fits. Because compared to the vast, howling emptiness of the main cavity, this cloud really is like a small patch of fluff, a compact, relatively dense for interstellar space, not of gas, that the Sun happens to be traveling through right now. The local fluff is around 30 light-years across, 30 light-years, in a bubble 1,000 light-years wide. It's a raindrop inside a cathedral, a small warm pocket tucked into the interior of the great cold clearing. Its temperature runs at around 30,000 Kelvin, still far hotter than anything you could survive, but a small fraction of the million-degree plasma of the surrounding bubble, and in the same way that 30,000 Kelvin is structurally different from 1,000,000 degrees, the local fluff is structurally different from the main bubble, denser, cooler, a distinct cloudlet with its own boundaries and its own motion through space. Near the local fluff is another cloudlet called the G cloud, slightly different in its properties, sitting in the same general neighborhood. The Sun is thought to be near the edge of the local fluff, possibly in the process of leaving it, though pinning down the exact boundary of something this wispy, this diffuse, is itself a genuine observational challenge. The point is simply this: you are not just inside the local bubble. You are inside the local bubble, inside the local interstellar cloud, inside the heliosphere, which is the Sun's own small magnetic bubble, the solar system's personal protective sheath against the interstellar medium, a structure we'll need to come back to because it becomes crucial to the final and most intimate part of this story. And it is crucial to keep those three things separate in your mind, if you can, because they are often confused in popular descriptions. The local bubble is the 1,000-light-year cavity, the 1,000-year-old cleared-out room blown by ancient supernovae. The local interstellar cloud, the local fluff, is the 30-light-year wisp the Sun is currently drifting through inside that room. The heliosphere is far smaller still. It stretches from the Sun to perhaps 100 astronomical units out, roughly 2 or 3 times the distance to the outermost edge of the solar system's defined boundary, a tiny sphere by interstellar standards, only about 0.02 of a light-year across. The heliosphere is the Sun's own output, solar wind and solar magnetic field pushing back against the interstellar medium, creating a bubble within a cloud within a cavity. 3 nested structures, 3 different scales, 3 different origins, the cathedral, the raindrop, and the lamp inside the raindrop. That's roughly where you are. The local fluff is real gas, real warmth in the context of the interstellar medium, but it is still staggeringly thin by any earthly measure. Its density runs at roughly 0.3 atoms per cubic centimeter, which sounds like something until you compare it to air at sea level, where you have around 27 million atoms per cubic centimeter. You could never feel the local fluff. You could never smell it, touch it, or sense it in any direct human way. It is there in the way that the faintest imaginable ghost of a ghost is there, present in the instruments, real in the physics, invisible to everything you are. And yet the Sun is moving through it. And the Sun was not always moving through it. Before the local fluff, there was different interstellar gas. After the local fluff, there will be other cloudlets, other thin wisps, other pockets and fingers of material floating in the interior of the bubble. The solar system's passage through the interstellar medium is not uniform. It is a drift through a landscape, a very thin, very hot, very empty landscape, but a landscape with texture, with structure, with patches and wisps and denser threads, all nested inside the enormous cleared cavity of the local bubble, all still slowly responding to the events that cleared that cavity in the first place. You are moving through all of this right now. The Sun is carrying you, along with every planet and moon and asteroid and comet in the solar system, through the local fluff, inside the local bubble, at a speed of about 20 kilometers per second, relative to the surrounding interstellar medium. In the time it takes you to read this sentence, 10 seconds perhaps if you're reading slowly, and letting it settle, the solar system has moved about 200 kilometers through the local fluff. And the local fluff itself, the whole 30 light-year wisp of it, is drifting through the interior of the bubble on its own trajectory. Everything is moving. Nothing in this story is still. The bubble is expanding, the shell is compressing, triggering stars. The Sun is drifting through the interior. The fluff is drifting too. The stars being born on the shell will eventually drift away from it on their own paths. The bubble will eventually stop expanding and be disrupted by other events, other supernovae, other pressures from the surrounding galaxy. Nothing here is frozen. It is all process, all motion, all time. And now, sitting inside the quiet of that motion, with the glow of a million-degree plasma around you, with every nearby stellar nursery clustered on the walls, with the Sun revealed as an accidental tourist who wandered in only 5 million years ago. Now the question hanging in the air is the one that was set up at the very beginning of all this. Who built the room? We've been circling it. The glow that Rosat found told us the gas inside was heated to impossible temperatures. The 3D dust maps and the clustering of molecular clouds on the shell told us the material was swept outward in a coherent wave. The still expanding boundary at 6.7 kilometers per second tells us the energy source is still echoing through the geometry. All of this points in one direction. One process produces these signatures. One kind of event concentrates this much energy into this kind of structure. Stars that explode, not just one, not just two, a whole sequence of them spread over millions of years, each one dying and adding its energy to the clearing, each one sweeping a little more gas outward, each one heating the interior a little hotter, each one contributing to the slow, sequential excavation of the 1,000-light-year room you live in now. The question is, which stars, where were they, can we find them? Can we trace backward from the cavity and the timing and the physics to the specific stellar populations that provided the bombs? And this is where the detective work of Kathryn Zucker and Alyssa Goodman and João Alves and their team, published in Nature in January 2022, becomes extraordinary, because they didn't just map the bubble, they didn't just confirm that supernovae dug it, they reconstructed the history, the timeline of events, the sequence of detonations, the slow 14-million-year excavation. And they traced it back to a neighborhood in the sky that is still visible tonight, a neighborhood you might have looked at without knowing what you were looking at. The Scorpius-Centaurus OB Association. You may have heard of it, or you may never have encountered the name. Either way, it deserves a moment. An OB association is a grouping of massive, bright, hot stars, the O-type and B-type stars that burn through their fuel in millions of years rather than billions, the short-lived giants of the galaxy. Scorpius Centaurus is the nearest large OB association to the solar system, a loose cluster of hundreds of massive young stars spread across a large swathe of sky, visible from the southern hemisphere and from lower northern latitudes. Within it, astronomers recognize several subgroups based on age and position. The two most relevant to the local bubble are Upper Centaurus Lupus and Lower Centaurus Crux. These are the surviving siblings of the stars that died. When a massive star lives and dies within an association like Scorpius Centaurus, it doesn't do so alone. It formed in a nursery with many others, and though each one burns at its own pace, the most massive ones burn fastest and die first. Over millions of years, the largest and most energetic members of the association reach the ends of their lives and explode as core collapse supernovae. The kind of explosion where a star's iron core can no longer support itself against gravity, collapses in less than a second, bounces, and drives a shockwave outward that obliterates the outer layers of the star and releases more energy in that moment than the Sun will emit across its entire 10 billion-year lifetime. The surviving members of Upper Centaurus Lupus and Lower Centaurus Crux are the ones that haven't died yet. They are the younger siblings, still burning, still visible. The older siblings, they'd be the most massive ones, the ones that went first. Those are the stars that exploded and hollowed out the local bubble. They are gone now, their material dispersed into the interstellar medium, their cores collapsed into neutron stars or black holes, but their family is still there. And by studying the living members of the association, look at their ages, their motions, their chemical compositions, researchers can work backward to reconstruct how many of the most massive members must have died, when, and where. The answer Zucker and colleagues arrived at was around 15 supernovae, give or take. The full range, the evidence supports, runs roughly from 14 to 20, depending on assumptions about the initial stellar population. Over the past roughly 14 million years, not simultaneous, not all at once. Spread over time, sequential, like slow drum beats in a long piece of music, each one adding energy to the cavity, each one pushing the shell a little further outward. 14 million years of supernovae. 15 deaths. One hole in space 1,000 light-years wide, still warm from the last of them, still growing from their combined momentum, still pressing new stars into existence on its walls. And some of those dead stars left traces behind. When the core of a massive star collapses, what forms is not always a black hole. Often, it is a neutron star, an object with roughly the mass of the Sun compressed into a sphere only about 20 kilometers across, spinning rapidly, generating enormous magnetic fields, beaming radiation into space like a lighthouse beam sweeping the dark. These are pulsars. And pulsars can be traced. They move. They carry the velocity imparted to them when their progenitor stars exploded, and by mapping their positions and tracking their motions backward, astronomers can sometimes find where they came from. One candidate, an inference rather than a certainty, and it is important to hold it as an inference, is a pulsar called Geminga. Geminga is one of the brightest gamma-ray sources in the sky, a neutron star remnant relatively close to the solar system, moving on a trajectory that some researchers believe could be traced back toward the Scorpius-Centaurus region over the relevant timescales. It may be the ghost of one of the stars that dug our bubble. Maybe. The kinematics are consistent. The certainty is not complete. What we can say is that the kind of stellar corpse we'd expect from the supernovae that carved the local bubble, a fast-moving neutron star from the right direction, of roughly the right age, exists in our neighborhood, and Geminga is the most prominent candidate. The stars that made this room may have left tombstones we can still find. And if you needed one more reminder that this is not abstract, that this is not merely a story about the sky, but a story about the ground beneath you, about the planet you are lying on, about the very deep sea floor, far below the surface of the oceans, we are getting close to that. Because some of those ancient supernovae didn't just carve the space around us, they rained on us. And the rain is still in the rock. But let's not arrive there too quickly. There's no hurry. The evidence will wait. It's been waiting 2.5 million years in the sediment at the bottom of the Pacific Ocean. A few more minutes won't change anything. For now, let the picture be complete in its first form. 1,000 light-year cavity, emptier than empty, glowing in million-degree X-rays that a satellite named for the discoverer of X-rays spent years mapping. Every molecular cloud near the Sun pinned to its walls like ornaments on the shell of a vast invisible balloon. Taurus, Ophiuchus, Lupus, Chamaeleon, Corona Australis, Musca, Pisces, all of them there because the explosion compressed the surrounding medium and gave them the density they needed to collapse into stars. The shell still expanding at 6.7 kilometers per second, still forming stars on its outer surface, still spreading the energy of detonations that concluded millions of years ago. The Sun, not at home here but passing through, a 5-million-year-old visitor who wandered in from elsewhere and happens to sit near the center by nothing more than the coincidence of its trajectory through the galaxy. And inside the bubble, inside the Sun's accidental position, a tiny wisp of warmer gas called the local fluff, 30 light-years across, which the Sun is currently drifting through. A raindrop inside the cathedral with the solar system's own heliosphere, far smaller still, humming its quiet protective hum inside the raindrop. 3 shells, 3 scales, 3 different kinds of nothing, each one slightly less empty than the one around it, like the layers of an extraordinarily rarefied onion, with you here at the center, warm, breathing slowly, still. Overhead, or underfoot, depending on where you are right now and which way your bed points, the stars on the walls of this great cavity are being born even as you rest. Clouds of gas are collapsing in Taurus, in Ophiuchus, in Lupus. New suns are forming tonight on the shell of an explosion that is 14 million years old and still hasn't quite stopped. You and those forming stars are part of the same structure. Different parts, different times, different scales, but carved from the same ancient event, nested in the same still warm aftermath. Let the picture settle like dust in still air. Let the scale grow quiet around you. It isn't a frightening scale when you sink into it. It is simply a very large version of the truth that you are never separate from the larger world, that the air you breathe and the oceans below you and the magnetic fields threading the solar system are all part of something immense and continuous, something that has been in motion for far longer than any mind can truly hold and will continue long after tonight is over. There is still more to this story. There is still the question of the builders, the sequence of their deaths, the fingerprints they left not just in the shape of space but in the rock. There is still the moment when this becomes not just the story of what is out there but the story of what has touched us here on the surface of this particular planet, this particular ocean floor, this Antarctic snow where even now a faint and ancient iron still drifts down from the exploded stars of our interstellar neighborhood. But that can come gently. For this breath, the shape is clear, the glow is accounted for, the walls are named. The sun has been placed in its true role, a wandering tenant in someone else's ancient ruin. The nurseries are found, pinned to the shell where the destruction became creation. And somewhere in the dark beyond this quiet, the next thread is waiting. The one about the rain, the radioactive rain, the iron from the hearts of dead stars, the fingerprints buried in the deep ocean floor. There's no need to rush toward it. Let the breath come and go, let the map rest. The Pacific Ocean floor has been keeping those secrets for 2.5 million years. It will keep them for a little longer while you drift. So let us begin with the builders.
Not the sun, not any star you can see from here, lying where you are right now. The builders are mostly gone, spent, collapsed, their cores crushed into dense, spinning embers or swallowed entirely into objects we can only infer by what bends around them. What they left behind is the room we live in.
And to understand the room, you have to understand something about the nature of the largest stars, about what they do at the end of their lives, and about how thoroughly, how violently, how completely they remake the space around them when they go. The most massive stars in the universe do not go quietly. You already know this in the way everyone knows it, but let's sit with the actual fact for a moment, because the fact is something that no casual mention can quite prepare you for. When a star much more massive than our Sun exhausts the nuclear fuel at its core, when it has burned through hydrogen, then helium, then carbon, and oxygen and silicon in a sequence of increasingly desperate interior fires, it reaches a point where the fusion cannot continue. The core, which has been pressing outward with the energy of those reactions, simply stops. And when it stops, gravity wins. Not gradually, not gently. In a fraction of a second, the core collapses. A volume of material that took millions of years to accumulate implodes in less time than you can blink. And then, because the infalling layers slam into the newly dense core and bounce, the outer layers of the entire star are thrown outward at a significant fraction of the speed of light. This is a core collapse supernova, and the energy released in that event is, by any measure you can apply, almost incomprehensible. In a matter of seconds, a single supernova releases more energy than our Sun will emit across its entire 10 billion year lifetime. The explosion shines so brightly that for weeks, sometimes months, a single dying star can outshine the combined light of hundreds of billions of ordinary stars. An entire galaxy's worth of steady, patient nuclear burning exceeded by one single ending. What concerns us here is not the light, it is what comes after the light. Because an explosion of that magnitude does not just radiate, it pushes, it drives a shockwave outward into the surrounding interstellar medium, that thin, cold, dark gas and dust that fills the space between stars, and it sweeps it aside the way a palm pressed flat against a tabletop, sweeps away scattered crumbs. The shock wave compresses whatever gas it encounters into a shell. Behind the shell, in the wake of the explosion, the material is heated to extreme temperatures and the density drops. You get, in short, a bubble. A hot, expanding, relatively empty sphere carved into the fabric of the interstellar medium. One supernova does this, carves a smaller bubble, maybe a few hundred light-years across, depending on the density of the surrounding gas. The shell expands, eventually slows, eventually merges back into the general ISM over millions of years. Ordinary enough in the context of a galaxy full of dying stars. But what if it is not one? What if it is many? A sequence of them, a series of explosions spread across millions of years, each one detonating inside or near the cavity carved by the last, reinforcing the walls, adding new energy to the expansion, scooping the interior ever emptier, and driving the shell ever further out. What do you get then? You get the local bubble. This is the picture that Katherine Zucker and her colleagues, Alyssa Goodman, João Alves, and the wider team behind their January 2022 paper in the journal Nature assembled with a degree of precision that previous generations of astronomers simply did not have the tools to achieve. They used three-dimensional dust mapping, a technique that allows researchers to reconstruct not just in 2 dimensions across the sky, but in genuine 3-dimensional depth, where the dense clouds of gas and dust in the local galaxy actually sit. And when you lay out the structure of all the nearby molecular clouds, the nearby star-forming regions, the nearby concentrations of young stellar material, something becomes strikingly, almost elegantly clear. They are not scattered at random, they are not distributed evenly through the volume around the Sun. They sit, essentially all of them, on a shell, on a surface, on the walls of a cavity. We talked about this before, the named nurseries pinned to the shell, Taurus and Ophiuchus and Lupus and Chamaeleon, and Corona Australis arranged around the local bubble's expanding perimeter, like decorations pressed into the rim of a bowl. But what Zucker and Goodman and Alves and the team did that was new, that was the advance in the 2022 paper, was reconstruct not just the current geometry, but the history. Using the positions and the motions of those clouds and the young stellar populations associated with them, they worked backward in time, like watching a slow-motion explosion in reverse, to ask when and where the bubble started. Their answer was approximately 14 million years ago. 14 million years. That is the figure to let rest in your mind for a moment. 14 million years before you closed your eyes tonight, the first of a series of enormous stars exploded in this region of the galaxy and began clearing what would eventually become our interstellar neighborhood. Our hominid ancestors were not yet a whisper of genetic possibility. Our entire genus did not exist. The continents were recognizable but not quite where they are tonight. And 14 million years ago, a massive star ran out of fuel, its core collapsed, and the first shock wave of what would become the local bubble began expanding outward into the Milky Way. But Zucker and colleagues did not find just one explosion. Their reconstruction of the bubble's history, working from the dynamics of the shell and the populations of stars associated with those progenitor regions, led them to a best estimate of roughly 15 supernovae over that 14 million year span. Roughly 15? The range extends, other analyses have suggested anywhere from about 14 to perhaps 20, depending on methodology and assumptions. But the central picture is the same. Not one catastrophic detonation, not even a few. A sequence, a drumbeat of death, spread across geological ages, each explosion adding to the last, each shockwave reinforcing and expanding the cavity carved by its predecessors. 15 stars, roughly, dying in sequence over 14 million years, and the room they left behind is the room we live in tonight. There is something quietly extraordinary about that arithmetic when you sit with it. The bubble's current diameter, that roughly 1,000 light-years, or 300 parsecs along its longer axis, that figure, that scale, is the accumulated result of approximately 15 separate stellar deaths. The emptiness you are suspended inside tonight, the hot, thin plasma glowing at 1,000,000 degrees across a volume that takes light itself 1,000 years to cross, is not the product of a single, violent moment. It is the product of a sequence of them, a slow, geological timescale demolition project carried out by stars that had no awareness of what they were doing and no intention of doing it. The universe does not intend, it only acts. So where did these builders come from? What were they? And is there any trace of them? Or of their relatives, the surviving members of the stellar family that produced them, still visible in the sky? The answer, which brings us to a piece of genuinely careful astronomical detective work, is yes. To understand it, you need to know something about how massive stars form. Massive stars, the kind that can end as supernova, do not generally form alone. They form in groups, clusters, and associations of young, bright, hot stars that emerge together from the same molecular cloud. These groupings are called OB associations, the designation referring to the spectral types O and B, which are the most massive and luminous categories of stars. They are bright, they are short-lived. A massive O-type star may exhaust its fuel in as little as a few million years, and they tend to form together in vast stellar nurseries. The nearest large OB association to the solar system is called the Scorpius-Centaurus Association, or SCOCEN for short. It is a grouping of young, hot, massive stars spread across a region of the sky in the constellations Scorpius and Centaurus, and it is divided by astronomers into 3 subgroups based on their ages and positions: Upper Scorpius, Upper Centaurus Lupus, and Lower Centaurus Crux. These are the surviving relatives, not the stars that exploded to carve the local bubble. Those are gone, their cores compressed into neutron stars or perhaps black holes, their outer layers long since dispersed into the medium around us. But the subgroups of the Scorpius-Centaurus Association, particularly Upper Centaurus Lupus and Lower Centaurus Crux, are the associations from which, as best as researchers including Dieter Breitschwert and colleagues in their own 2016 Nature paper, and Burkhard Fuchs and colleagues in earlier work, could determine the progenitor stars of the local bubble descended. The stars that died were members, or cousins, or earlier generations of the same stellar family whose younger, still living members you can see tonight in the southern sky if you are in the right part of the world. This is the detective work that deserves a slow breath. You cannot go back and watch the supernovae happen. They detonated millions of years before anyone was here to observe them. But you can, with careful measurements of stellar positions, velocities, ages, and the dynamics of the gas, trace the trajectories backward. You can ask, if I reverse the current motion of these stellar populations, if I account for the motion of the gas and the expansion of the shell, where do the arrows point? And the arrows, according to Breitschwert and colleagues and the work that informed and built on theirs, point back to the Scorpius-Centaurus Association. The bombs came from there. The surviving siblings are still there, still burning, still massive and young and brilliant, and will themselves eventually die in supernovae of their own and continue carving and reshaping the local interstellar medium long after tonight is over. There is something almost familial about this. The stars that died are gone. The stars that share their parentage are still alive. And the room the dead ones carved, we are inside it now. The stars died, but they did not disappear entirely. Core collapse supernovae do not leave nothing. When the outer layers are thrown outward, the core, the compressed remnant, remains. If the core is of certain masses, it becomes a neutron star, an object roughly the size of a city, perhaps 10 to 20 kilometers across, but containing more mass than the Sun, so dense that a teaspoon of its material would weigh hundreds of millions of tons, spinning sometimes dozens or hundreds of times per second, beaming radiation from its magnetic poles like a lighthouse. These spinning neutron stars, when their beams sweep past us, we call pulsars. Some of the supernovae that carved the local bubble should, by this logic, have left neutron star remnants, and some of them, researchers suspect, may still be identifiable, inferred from their positions, their velocities, the way they track back through space to the general region and time frame of the local bubble's formation. One of the most frequently mentioned candidates is Geminga. It is a pulsar, a neutron star, sitting at a distance of roughly 800 light-years, well within the broader local bubble region. Its name is something of a cosmic joke. It derives from a Milanese dialect phrase meaning roughly "it's not there," a reference to the fact that when astronomers first detected its X-ray and gamma-ray emission, they could not find any corresponding optical source, nothing visible, just this energetic, pulsing signal from something that to ordinary telescopes was not there. Geminga was eventually identified as a pulsar, a spinning neutron star, and its properties, its age, its velocity, its trajectory when you trace it backward through space, are consistent with it being a remnant of one of the supernovae that contributed to the local bubble. Consistent with? That phrasing matters, and it deserves emphasis. You cannot stand at the scene of a demolition and know with absolute certainty which particular stick of dynamite from 14 million years ago produced which particular crack in the wall. The velocities carry uncertainties, the ages carry uncertainties, the original positions of the progenitor stars can only be estimated. Geminga is a candidate, a plausible candidate, supported by the circumstantial evidence of its kinematics and its age and its location. Other nearby pulsars have been suggested as well, but the specific identification, this neutron star from this particular supernova, the fourth in the sequence, which detonated approximately 9 million years ago, is beyond what the current evidence can firmly establish. What you can say is that the neutron star remnants of the local bubble's builders should still be in the vicinity, and that Geminga and objects like it are the best candidates we have. The grave markers are there, we just cannot yet read all their inscriptions with full certainty. There is something else worth pausing on here, because it tends to surface when people first learn about the local bubble, a tempting story, one that feels satisfying and almost mythological, which is precisely why it is worth examining carefully and setting aside. The temptation is this, to say that the supernovae cleared a space for us, that they excavated a safe, relatively empty region of the galaxy, free of the dense molecular clouds that can be hazardous to planetary systems, and that into this cleared and hospitable cavity the solar system arrived and set up its household, and that we owe our existence, or at least some comfortable aspect of it, to those long-ago explosions. It is a beautiful story. It is the kind of story the human mind reaches for naturally, the kind that makes the universe feel purposeful and kind, as though the largest scales of physics are somehow arranged with us in mind. It is not, however, what happened. The Sun entered the local bubble approximately 5 million years ago. The bubble itself had been forming and expanding for roughly 14 million years by the time the solar system wandered in. The solar system did not form inside the bubble. The Sun's current position near the center of the cavity is not the result of being placed there, or of being drawn there, or of any property of the Sun that made the bubble a fitting home. It is the result of the Sun's ongoing motion through the galaxy, a long, slow orbit around the galactic center, carrying the solar system through varying regions of the interstellar medium over billions of years. Combined with the simple fact that the local bubble is large, roughly 1,000 light-years across, and things that are large in a neighborhood tend to be encountered eventually. We wandered in. Roughly 5 million years ago, the solar system crossed whatever boundary then defined the bubble's edge and entered the hot, thin, low-density interior. And because the bubble is large and because the sun's trajectory and speed are what they are, the sun has drifted toward the center. But the center is not a special place. There is nothing at the center anchoring the sun. It is coincidence. Cosmic coincidence of the most ordinary kind, the kind the universe produces in enormous quantities simply by having a lot of matter in motion over a lot of time. This matters not just because accuracy matters, though it does, it matters because the alternative, the story in which the bubble was cleared to make room for us, would require the universe to have intended something. And the universe, as best we can determine from everything we can observe and measure, does not intend. Stars form from the physics of gravity and gas dynamics and turbulence. They live according to the physics of nuclear fusion and radiation pressure and stellar evolution. They die according to those same laws applied to the end state of their cause. The cavity they left behind exists because of fluid dynamics and thermodynamics, not because of purpose. We are not the point of the story, we are passengers in it, and honestly that is more interesting. A universe that's shaped to shelter for us would be a cozy and parochial universe, a small universe at heart despite its size, a universe in which we are coincidental tenants inside an accidental ruin carved by the physics of dead stars. That is a stranger, larger, more genuinely astonishing universe. And we get to live in it, which seems somehow like the better end of the arrangement. Now, we are inside the local bubble. The sun is a tourist, a wanderer who entered this vast, low-density region about 5 million years ago and has been drifting through it ever since. But the solar system does not simply move through the bubble as if through a uniform, empty room. The interior is not truly uniform. There are wisps, cloudlets, small concentrations of gas that are slightly denser and slightly cooler than the surrounding million-degree plasma, relics of the turbulent mixing of the supernova heated gas with whatever cooler material was present and survived. And right now, tonight, the solar system is moving through one of those wisps. It is called the local interstellar cloud. Sometimes, and this is a name worth holding for a moment, it is called the local fluff. The local fluff. That name deserves a quiet smile because it is both perfectly accurate and perfectly understated. This is a cloudlet of gas warmer than the hot bubble interior, around 30,000 Kelvin, which sounds extreme until you remind yourself that the surrounding bubble plasma runs at approximately 1,000,000 degrees and slightly denser at around 0.3 atoms per cubic centimeter. That density is still far below what you would encounter in a typical molecular cloud, far below what you could detect with your senses in any meaningful way. But it is measurably, detectably different from the thinner plasma surrounding it. The local interstellar cloud is approximately 30 light-years across. 30 light-years. In the context of the local bubble, which spans something like 1,000 light-years at its widest, that is, and let us be precise about the picture this calls for, like a small raindrop hanging inside a cathedral. The cathedral is the local bubble. Vast, airy, its walls distant, its interior mostly empty space, warm to temperatures beyond anything your body could register as anything other than instant annihilation. And inside that cathedral, drifting, is a small raindrop, 30 light-years across. And inside that raindrop, the solar system. Inside the raindrop is where you are tonight. Near the local interstellar cloud, adjacent to it, perhaps connected to it, the boundaries between these cloudlets are not sharp lines but gradients, is another small concentration of gas called the G-cloud. The G-cloud and the local interstellar cloud are neighboring cloudlets in this patchwork of slightly denser wisps inside the larger cavity. The Sun is currently within or very near the local interstellar cloud, and the G cloud lies just ahead in our trajectory if you could somehow watch the solar system's motion on a sufficiently slow timescale, slow enough that millions of years of drift were compressed into a few minutes of observation. It is important. This is a point worth spending a moment on because the conflation is extremely common and genuinely confusing. To keep the local interstellar cloud and the local bubble clearly separate in your mind from another bubble entirely, that other bubble is the heliosphere. The heliosphere is the Sun's own bubble, not a hole in the interstellar medium, but a structure created by the Sun itself. The volume of space within which the Sun's solar wind, a continuous stream of charged particles flowing outward from the Sun in all directions, is strong enough to hold back the pressure of the surrounding interstellar medium. The heliosphere is enormous by any human measure. It extends perhaps 100 astronomical units from the Sun in some directions, which means it encompasses the orbits of all the planets and extends far beyond even the outermost reaches of the recognized solar system. But compared to the local bubble, it is minuscule. The heliosphere is a sphere roughly a few hundred astronomical units across. The local bubble is roughly 1,000 light-years across. 1 light-year is approximately 63,000 astronomical units. The local bubble is millions of times larger than the heliosphere. The heliosphere is the solar system's immediate protective envelope, a bubble created by the Sun's own activity pressing outward against the local interstellar medium. In this case, against the gas of the local interstellar cloud, through which the solar system is currently moving. The local bubble is the vast interstellar cavity carved by supernovae over 14 million years. One is a breath, the other is a room. One is the Sun's own effort, the other is the inheritance of dead stars. Keep them separate and the story makes sense. Conflate them and you have two very different things wearing the same name and causing nothing but confusion. The heliosphere is the shell of the solar system's own making. The local bubble is what it sits inside. And the local interstellar cloud, the local fluff, the 30 light-year raindrop we are currently passing through, that sits between the two. It is a cloudlet inside the local bubble's cavity, and the heliosphere presses against its gas from within, maintaining the boundary between the Sun's domain and the local interstellar environment. So here, in summary, is where you are tonight, inside the heliosphere, the Sun's own bubble, the outermost boundary of the solar system's immediate magnetic domain, measured in hundreds of astronomical units. Inside the local interstellar cloud, the local fluff, 30 light-years across, a wisp of warmer, slightly denser gas drifting through the interior of the local bubble. Inside the local bubble, the local cavity, roughly 1,000 light-years across at its longest extent, carved by approximately 15 supernovae over 14 million years, its interior maintained at around 1 million degrees by the heat of those ancient explosions, its walls studded with the star-forming nurseries whose young molecular clouds the expanding shock waves swept up and compressed. 3 nested structures, 3 different scales, the smallest built by the Sun, the middle one a wisp, just coincidentally in your path, the largest built by dead stars over geological ages, and you and the Sun and the entire solar system just passing through. Sit with that nesting for a moment. You do not have to hold every number, just the picture. A small raindrop inside an enormous cathedral, and you inside the raindrop. That is not a metaphor for something smaller or cozier than reality. That is a description of the actual structure of the space around you, tonight, wherever you are lying still and letting the darkness settle. The cathedral is still warm. The warmth comes from fires that burned out millions of years ago, and the air in the cathedral is still carrying that heat, still glowing faintly in X-rays that no human eye can see, but that the Rosat satellite, the Röntgen satellite, named for the discoverer of X-ray radiation and launched in 1990, detected and mapped across the whole sky. Rosat was designed to survey the X-ray sky to find and catalogue the sources of high-energy radiation across the universe. And among the things it found was a diffuse, soft X-ray background. Not from any one source, not from any one object, but from the whole interior of the local bubble, from the hot plasma filling the cavity, from the million-degree gas left behind by the supernovae that carved it. The cathedral glows. You cannot see the glow, but it is there, and the instruments built by human hands and placed in orbit above the atmosphere have read it. And that reading is part of what tells us the bubble is real. There is a nuance worth naming here, because honesty about the complexity of the science is, in the long run, more interesting than a perfectly clean story. The soft X-ray background observed by Rosat was initially attributed almost entirely to the million-degree gas of the local bubble. And a good portion of it is. But more recent analysis, work done with sounding rockets and refined observational techniques after Rosat, including work that helped disentangle different contributions to the X-ray signal, revealed that some of the diffuse X-ray glow comes from closer in, from a process called solar wind charge exchange. The sun's solar wind, a stream of charged particles flowing outward from the sun, can interact with neutral atoms inside the solar system itself, atoms that drift in from the local interstellar medium. And those interactions produce soft X-ray emission. Not from the hot bubble gas, but from the solar system's own immediate environment. What this means is that the bubble's signature in X-rays is real, but somewhat more complicated than the initial picture suggested. The local bubble's million-degree gas is genuinely there, genuinely glowing, genuinely the thermal remnant of the supernova shocks that carved the cavity. But the amount of that glow contributed by the bubble versus by solar wind charge exchange is something researchers have worked to carefully separate. The bubble is not diminished by this refinement, it is clarified by it. The science is doing what good science does, adding precision and nuance to an earlier, rougher picture. We live inside a cathedral that glows in X-rays that are partly the lingering heat of dead stars and partly the ongoing interaction of our own sun's wind with the local gas through which we move. Both are real, both are happening right now, and both are, in their way, remarkable. The carvers are gone. The room stands. The walls are being rebuilt by the new stars forming along the perimeter. Young stellar nurseries pressed into existence by the same expanding shell that the supernovae drove outward over millions of years. The interior still runs warm. The surviving relatives of the bombs, the young massive stars of the Scorpius-Centaurus Association, burn on in the southern sky, themselves on a countdown that in astronomical terms is not too far off. And somewhere in the vicinity, spinning in the dark, Geminga and objects like it, the compressed, dense, city-sized remnants of the stellar cores that collapsed, the neutron stars that the explosions left behind like embers, wait to be definitively identified as the remnant gravestones of the builders. Something is missing from this picture though, or rather, not missing. Waiting. The story of the local bubble is not only a story of what is out there in the space around the solar system, it is also a story of what landed here, of what, from those distant stellar deaths, arrived at this planet, of what is sitting right now in the deep ocean trenches and on the Antarctic ice, and in the rock below both of them, carrying the fingerprints of stars that exploded before any ancestor of yours stood upright on any savanna. There is a kind of iron at the bottom of the Pacific Ocean that should not be there. It should not be there because it does not come from Earth, It does not form in significant quantities in any ordinary geological or atmospheric process. It is an isotope, a particular variant of the iron atom called iron-60. The nucleus of an ordinary iron atom contains 26 protons and 30 neutrons. Iron-60 contains 26 protons and 34 neutrons. That extra mass makes it unstable. It is radioactive, and it decays. With a half-life of approximately 6 million years, iron-60 transforms itself over time into the stable isotope cobalt-60, emitting radiation as it goes. 2.6 million years is a long time by human reckoning. It is not very long at all by geological reckoning, and it is precisely long enough to be interesting because it means that iron-60 deposited in the ocean floor or in Antarctic snow millions of years ago is mostly gone by now. But not entirely. Not if enough of it was deposited. And the question researchers asked and then found answers to was, where did the iron-60 come from, and when did it arrive? It came from supernovae. Iron-60 is produced in the interiors of massive stars during their final, most energetic stages of fusion, and it is released into the interstellar medium when those stars explode. It is not produced in any significant quantity on Earth. It is not produced by cosmic ray interactions with ordinary rock at rates that would explain the concentrations found. It is, essentially, a fingerprint. If you find iron-60 somewhere, you are finding a record of a nearby supernova, and researchers have found it. Beginning with work by Klaus Knie and colleagues in 2004 and expanded significantly by Anton Wallner and colleagues in their 2016 paper in the journal Nature, iron-60 has been detected in deep-sea ferromanganese crusts, those slow-growing mineral deposits that form on the ocean floor over millions of years, accumulating layer by layer at a rate so slow that a single centimeter of crust might represent hundreds of thousands of years of deposition. They have been found in Pacific Ocean sediment cores. They have been found in lunar samples. The Moon, with no atmosphere and no geochemical processing of its surface, preserves the record of what falls on it with particular fidelity. And in work published in 2019 by Dominic Cole and colleagues in Physical Review Letters, iron-60 was detected in fresh Antarctic snow. Not in ancient ice, in snow that fell recently enough to still be accessible from the surface, which means it is not merely a record of ancient events. Iron-60 is still arriving on Earth today. That last detail has a particular quality to it. The ancient iron in the ocean floor, 2.5 million years old, speaks to a specific set of events in the distant past. But the fresh iron in the Antarctic snow speaks to something ongoing, to the fact that the solar system is still moving through the enriched interstellar medium left behind by those supernovae, still sweeping up the dispersed debris of stellar deaths that happened millions of years before today, still accumulating the radioactive fingerprints of the local bubble's builders as it drifts through what they left behind. The rain has not stopped. It is quieter now. Trace amounts, not the pulse of those ancient deposition events. But it continues. And in the ocean floor record, the timing of the deposition tells a more specific story. There are not one but two distinct peaks. Two episodes of elevated iron-60 concentration, separated in time. One centered around 2.5 to 3 million years ago. Another, older one, around 6.5 to 8 million years ago. Two pulses of radioactive iron from the sky. Two events. And the distances implied by the decay, by how much iron-60 survived the journey to Earth, given its 2.6 million year half-life, suggests supernovae at distances of roughly 150 to 300 light-years, which translates to about 50 to 100 parsecs. Close. Well, within the local bubble. Close enough that the shock waves and the stellar ejecta reached Earth, settled into the ocean, were buried under subsequent layers of slow mineral deposition, and waited there, quietly decaying for us to eventually come along with our instruments and find them. Two events kept separate the older pulse, 6.5 to 8 million years ago, from an earlier supernova or cluster of supernova within the forming bubble. The more recent pulse, 2.5 to 3 million years ago, from a closer or more energetic event or set of events that deposited a measurable layer of cosmic iron across the ocean floor of this planet. 2.5 to 3 million years ago. That timing will become important. But the reign of iron is already extraordinary on its own, even before you follow the timing to where it leads. Because what you have in those deep-sea crusts and those Pacific cores and those lunar samples is something almost beyond the ordinary register of remarkable physical material from a supernova. Not an image of a supernova, not a spectrum or a signal or an inferred quantity. Actual atoms. Actual iron-60 atoms synthesized inside the core of a star that exploded in the local bubble, expelled into the interstellar medium, carried across the void by the expanding shockwave and the general drift of the enriched gas, eventually swept up by the solar system as it moved through that interstellar medium, caught by Earth's gravity and settled into the ocean. Those atoms are there. They are in rock that human hands have retrieved from the ocean floor. They have been measured by mass spectrometers in laboratories. They are sitting still in those samples. The stars built you from their own material. All the iron in your blood traces back to stellar nuclear synthesis, to ancient supernovae far older than the solar system. But the iron in the ocean floor at 2.5 million years old is something slightly different. It did not go through the solar system's formation. It did not get incorporated into planets or life. It arrived after. It is a late delivery, a package of radioactive material that fell from the sky in geological time, a remnant of the specific dead stars in the specific region of the galaxy that the solar system happens to be passing through right now. You live in a blast zone, a very old, very quiet, still, slowly decaying blast zone, and the evidence is in the rock. And here is where the story takes one more turn, because the ocean floor is not the only place this radioactive iron has been found. In 2019, a team of researchers published results from a rather remarkable set of samples. Not deep-sea crusts, not Pacific cores, not lunar regolith, but Antarctic snow. Fresh Antarctic snow. Snow gathered from the surface of the ice, the kind that fell in recent decades, not geological time. And buried in that fresh white snow in quantities so small they required accelerator mass spectrometry to detect at all, was iron-60, the same isotope, the same supernova fingerprint. Danielle Cole and colleagues published those results in Physical Review Letters in 2019, and what they showed was that the delivery is not just a thing that happened, it is a thing that is still happening. Right now, as the solar system moves through the interstellar medium of the local bubble, the enriched gas of that cavity, gas that was expelled and stirred and seeded by those ancient explosions, is still being swept up, still arriving. The iron atoms falling into Antarctic snow today are not from a recent supernova. There has been no nearby explosion in recorded human history, no stellar death close enough to reach us. What is falling now is the lingering residue, the last thin wisps of a contamination event that began millions of years ago and has not yet fully cleared. The concentration is minuscule, there is no harm in it, but the fact of its presence means the solar system is still inside the aftermath, still passing through the debris field. The bombs went off long ago, but you are still crossing the ground where they fell. Take a moment with that. The snow that fell on Antarctica last winter carries iron from dead stars. Not metaphorically, not poetically in the sense that all iron comes ultimately from stars, which is also true. Literally, iron-60, with its half-life of roughly 2.5 million years, an isotope your own planet does not produce, an isotope that could only have come from a supernova in your cosmic neighborhood, is settling onto the surface of Earth right now. It lands on the ice sheets. It washes into the ocean. It accumulates grain by grain at a rate so slow it is almost incomprehensible, but it accumulates. There is a kind of quiet vertigo in that. You do not need a telescope to touch the local bubble. It is touching you now. The deep-sea record, as we have been exploring it, does not show a single uniform layer of iron-60 enrichment. It shows two distinct pulses, two separate windows of elevated deposition, each corresponding to a different cluster of supernova events at somewhat different times. And keeping those two pulses distinct matters because they are telling slightly different parts of the same long story. The older of the two pulses sits in the geological record at roughly 6.5 to 8 million years ago. This is the earlier wave, the first detectable enrichment in the ferromanganese crusts, and it corresponds to a period of stellar death associated with the earliest excavation of the local bubble's cavity. The stars that exploded then were among the first of the Scorpius-Centaurus Association's most massive members to reach the end of their short, brilliant lives. They were probably not more than 150 to 300 light-years away, 50 to 100 parsecs in the astronomers' preferred units, close enough for their expelled iron-60 to reach Earth in detectable quantities, but far enough that the bombardment was dilute, spread thin across the interstellar medium before it arrived. The younger pulse, the stronger, more clearly defined one, is centered around 2.5 to 3 million years ago. This is the one Anton Wallner and his colleagues pinpointed with particular care in the 2016 study published in Nature. It is more sharply defined in the sediment record, more concentrated, and it corresponds to a set of supernovae that were, if anything, somewhat closer. Still within that range of roughly 50 to 100 parsecs, still members of the extended stellar nursery that the Scorpius-Centaurus Association represents, stars that formed together from the same great cloud and are now, generation by generation, dying together, each explosion helping to dig and maintain the very cavity that the solar system is currently traversing. 2.5 million years ago, that number is worth holding for a moment because it lands the story somewhere very specific. 2.5 million years ago on this planet, the genus Homo was just beginning to emerge from its Australopithecine ancestors on the African savannas. The Pliocene epoch was ending, the world was cooling, and somewhere overhead, not visible in the night sky as an extraordinary event because the distance of 100 or more light-years is enough to reduce even a supernova to something roughly the brightness of the moon at most, briefly, then fading. One or more massive stars were completing their lives and sending their material outward in all directions. Some of that material was iron-60. Some of that iron-60 drifted across the void and fell, over thousands of years of slow accumulation, into what would eventually become the deep ocean floor. Your distant ancestors, if they had looked up on those nights, might have seen something brighter than usual in the sky. A new star, they might have thought. A wandering light. They had no framework for what it actually was. They did not know they were watching the continued excavation of the cave they already lived in. And this is where the timing link becomes something more than just interesting, because 2.5 to 3 million years ago is also within the imprecision of geological dating, approximately when something significant began happening to Earth's climate. The planet was sliding into the Pleistocene glaciation, the Ice Age in the popular sense, the long cycle of advancing and retreating glaciers that would define Earth's climate for millions of years, and that technically, in geological terms, has not entirely ended, was beginning. And some researchers have looked at that coincidence and asked a very careful, very serious question. Could those supernovae have contributed to the cooling? Let's be very clear about what that question means and what it does not mean. The evidence for the timing correlation, the iron 60 pulse at roughly 2.5 to 3 million years ago overlapping with the onset of intensified glaciation, is real. That overlap is documented. It is in the data. What is not settled, what remains an active area of research and genuine scientific debate, is whether there is a causal mechanism connecting the two. Timing overlap is not proof of cause. Two things happening at the same time does not mean one caused the other, but the proposed mechanism is interesting enough and plausible enough to be worth walking through carefully. Here is the basic idea. The solar system is not simply moving through space naked, it carries a protective structure with it, the heliosphere. Now, it is very important not to confuse the heliosphere with the local bubble. They are entirely different things at entirely different scales. The local bubble is a cavity in the interstellar medium roughly 1,000 light-years across. The heliosphere is the region of space dominated by the Sun's solar wind, the stream of charged particles flowing outward from the Sun in all directions, carving out a bubble of solar influence that extends somewhere between roughly 100 and perhaps 200 astronomical units from the Sun in various directions, depending on the local conditions outside it. At that scale, the heliosphere is tiny compared to the local bubble. It is, in our cathedral analogy, not even the raindrop. It is a mote of dust inside the raindrop. The heliosphere is the Sun's own immediate personal space, while the local bubble is the vast empty room the whole solar system is crossing. But the heliosphere matters for Earth because it acts as a partial shield. The solar wind it generates pushes back against the interstellar medium, against the flow of interstellar gas and the flux of galactic cosmic rays, high-energy charged particles streaming in from distant supernovae and other energetic events throughout the galaxy. The heliosphere deflects some portion of those cosmic rays, reducing the dose that reaches the inner solar system and Earth's atmosphere. The degree of shielding varies depending on how strong the solar wind is and how dense and pressurized the surrounding interstellar medium is. If you increase the external pressure, if the solar system passes through a denser or more disturbed region of the interstellar medium, the heliosphere gets compressed. It shrinks, and a smaller heliosphere lets more galactic cosmic rays through. Monica Ofer and colleagues, in work published in Nature Astronomy in 2024, modeled what would happen if the solar system had passed through a particularly dense interstellar cloud, or through interstellar gas significantly disturbed and enriched by nearby supernovae around 2 to 3 million years ago. Their models suggested that the heliosphere could, under those conditions, have been compressed dramatically, potentially reduced to a fraction of its current size, and if that happened, Earth would have been exposed to a significantly elevated flux of galactic cosmic rays. Now, what do cosmic rays do when they hit Earth's atmosphere in greater numbers? This is where the science gets genuinely contested, and intellectual honesty requires sitting in that uncertainty rather than resolving it prematurely in either direction. One hypothesis, associated with Henrik Svensmark and his colleagues, and still the subject of active research and significant debate within the scientific community, is that galactic cosmic rays influence cloud formation. The idea, simplified, is this: cosmic rays are energetic particles. When they crash into the atmosphere, they ionize air molecules, creating ions. Those ions can act as condensation nuclei, seeds around which water vapor clusters to form cloud droplets. More cosmic rays, in principle, could mean more ions, more condensation nuclei, more low-level cloud cover. And more cloud cover means more of the sun's energy is reflected back into space before it reaches the surface. More reflection means cooling. A compressed heliosphere, more cosmic rays, more clouds, lower temperatures, ice. It is an elegant chain of reasoning. It is also contested. The empirical evidence for the cosmic ray cloud nucleation link is debated. Laboratory experiments and observational studies have produced mixed results. Some researchers find the effect real but small. Others are skeptical that it is large enough to drive significant climate change. The scientific community has not reached consensus on whether the Svensmark mechanism is a primary driver, a contributing factor, or a negligible one. What is not contested is the iron 60 timing. The deposition happened, the pulse is real, the blasts were close, the heliosphere, if compressed by the disturbed medium those supernovae created, would have let more cosmic rays through. Whether that was enough to tip Earth into a glacial cycle is the open question. It is a fascinating open question. It is the kind of question that keeps researchers up at night, building better models and hunting for better proxy records in the geological archive. But it is not a settled answer, and presenting it as one would be misleading. What we can say, honestly, is this. Approximately 2.5 to 3 million years ago, one or more massive stars exploded at a distance of roughly 100 to 300 light-years from Earth. Those explosions left radioactive iron in our ocean floors and in our lunar samples. Those same explosions disturbed and enriched the interstellar medium through which the solar system was moving. The heliosphere was potentially under different, more challenging external conditions at that time. Earth's climate was, at approximately the same time, entering a long period of glaciation. The threads connect. Whether they constitute a causal chain remains an open and genuinely important scientific question. The correlation is real, the mechanism is plausible, partially supported, and actively being tested. That is where the science actually stands. And there is something honest and even beautiful about that position. The universe is under no obligation to give us tidy answers on our timescales. The researchers working on this, the geophysicists measuring isotope ratios in crustal samples, the climate modelers reconstructing ancient atmospheric conditions, the heliospheric physicists running simulations of what the outer solar system would have looked like under different external pressures, are doing the painstaking, incremental work of actually finding out. That work is ongoing. The story is not finished. There is one more thing worth addressing directly because it comes up in popular discussions of this topic, and it deserves a clear, honest response. Could a supernova in our galactic neighborhood pose a serious threat to Earth today? The question is natural. We have spent this entire journey learning that stellar explosions shape the cavity we live in, rained radioactive material onto our planet, and possibly contributed to a major climate shift. The leap to "are we in danger?" is understandable. The answer, as best as science currently understands it, is no, not from the local bubble's ancient history, and not from any immediate source in our current neighborhood. The explosions that carved the local bubble happened millions of years ago. The Scorpius-Centaurus OB association, the stellar nursery that produced the progenitor stars, is still there. It still contains massive stars. It will produce more supernovae in the future. But it is several hundred light-years away, and a supernova at several hundred light-years is not a civilization-ending event. The generally discussed threshold for serious biological harm from a nearby supernova is on the order of about 25 to 30 light-years. An event that close could pose a significant threat to the ozone layer and expose life to elevated radiation levels. The nearest massive stars capable of going supernova in the cosmically near future are not that close. Betelgeuse, that red supergiant you can find in Orion's shoulder, is roughly 700 light-years away. It is a spectacular candidate for eventual supernova, but at that distance, when it goes, whenever that is, and it may be hundreds of thousands of years from now or more, it will be a remarkable celestial event. It will not be a catastrophe for life on Earth. We are, in a sense, in a protected period. The wave of supernova activity that carved the local bubble is largely past. The bubble is still expanding, but slowly. the Iron 60 raining onto Antarctic snow is a trace, a ghost signal, not a fresh bombardment. The heliosphere is intact and doing its job. The Sun is a middle-aged, stable star sitting in the quiet interior of a blast zone that has mostly finished blasting. There is no present threat to dramatize here. The drama is entirely in the past, a deep, strange, magnificent past that has nonetheless left physical fingerprints on the world you inhabit. And that, in the end, is what makes the local bubble genuinely worth knowing about. Not fear, not alarm, something almost the opposite of that. Consider what the full picture looks like now that we have walked all the way through it. 14 million years ago, 14 million years, a span so large that it encompasses the entire evolutionary history of the ape lineage that would eventually produce your species. A sequence of massive stars in what we now call the Scorpius-Centaurus-OB association began reaching the ends of their lives. They were enormous, hot, brilliant, burning through their fuel at rates so prodigious that what took our sun billions of years to consume, they went through in mere millions. And one by one, over that long sequence of stellar time, they exploded. Each explosion sent a shockwave outward at thousands of kilometers per second, a wall of energy and material plowing through the surrounding interstellar medium, scooping up gas and dust and sweeping it into an expanding shell. The first few explosions started a cavity, the later ones expanded it. Over roughly 14 million years, something like 15 of these cataclysms, give or take, the count is approximate, and the work of tracing individual events from the surviving record is painstaking, hollowed out a region of space now roughly 1,000 light-years across in its longest dimension, not a perfect sphere. A peanut shape, roughly, irregular, open toward the galactic halo at the top. The walls of that cavity are not empty. They are dense with the swept-up material of those explosions, and it is on those walls, on the compacted shell of 1 million years of stellar violence, slowly decelerating into ordinary interstellar matter, that the nearest star-forming regions now sit. Taurus, Ophiuchus, Lupus, Chamaeleon, Corona Australis, the places where new stars and new planetary systems are being born today. The cavity made the nurseries. The death of old stars is directly causing the birth of new ones. Inside that hollow, the gas that remains, the thin, hot plasma that did not get swept into the walls, glows at roughly 1 million degrees. It is detectable in soft X-rays, and it is how the Rosat satellite first clearly mapped the structure in the 1990s, though later work has refined our understanding of how much of that X-ray glow comes from the bubble itself, and how much from solar-wind interactions closer to home. The interior is almost incomprehensibly empty by any terrestrial standard, about 5/100ths of an atom per cubic centimeter, 10 times emptier than the ordinary interstellar medium around which we built our intuitions about what space is like between stars. Into this vast, quiet, still, slowly expanding crater about 5 million years ago, the solar system wandered. It did not build the bubble. It had nothing to do with the excavation. The explosions had already happened, the cavity was already formed, the shell was already there, and the sun, then as now, a rather ordinary yellow dwarf on its long orbit around the galactic center, happened to cross the boundary and enter. Pure coincidence, pure geometry. The solar system is a traveler that walked into someone else's ruined building and happened to find itself near the center of the ruins. Within the larger bubble, we ride a smaller cloud, the local interstellar cloud, the one sometimes called the local fluff, a wisp of warmer and marginally denser gas only about 30 light-years across, at about 30,000 degrees. And next to that cloud, the G-cloud, small neighborhoods within a vast empty district. And within that small cloud, the heliosphere, the sun's personal magnetic domain, a structure that would fit inside a grain of sand if the local bubble were the size of this room. At every level of scale, the nesting is vertiginous. The explosions that made the cavity left their mark on this planet. Iron-60, an isotope that cannot be made here, that decays with a half-life of 2.5 million years, and therefore cannot be a relic of the solar system's own formation, has been found in ferromanganese crusts dredged from the deep ocean floor. It has been found in sediment cores from the Pacific. It has been found in samples returned from the surface of the Moon. And it has been found, in the most recent and in some ways most striking discovery, in fresh Antarctic snow. The deposition record shows two distinct pulses, one centered around 6.5 to 8 million years ago, one centered around 2.5 to 3 million years ago, each from different supernovae at distances of roughly 50 to 100 parsecs, roughly 150 to 300 light years. Close enough to reach us, close enough to leave evidence. And the pulse at 2.5 to 3 million years ago overlaps, within the imprecision of geological time, with the onset of the Pleistocene glaciation. The timing is documented. The proposed mechanism, a heliosphere compressed by passage through supernova-disturbed interstellar medium, admitting more galactic cosmic rays, potentially influencing cloud formation and therefore surface temperatures, is actively being studied. It is a plausible chain. It is not a proven one. The science is ongoing. The question remains genuinely open, and that openness is not a weakness in the story, but a sign that the story is still being investigated by real researchers using real data from the real ocean floor. All of this is verifiable. All of it is in peer-reviewed literature. Catherine Zucker, Alyssa Goodman, and João Alves, working with 3D dust maps of the galaxy's local neighborhood, published the most comprehensive reconstruction of the bubble's history and geometry in Nature in January 2022. Dieter Breitschwert and colleagues traced the supernova history back to the Scorpius-Centaurus Association and connected it to the Iron-60 record in a companion Nature paper in 2016. Anton Wallner and colleagues documented the two distinct deposition pulses and their timing in the same year. The names, the dates, the isotope measurements, the dust maps. These are real. The bubble is real, and it is still here. Still surrounding you. The walls are still there, 3 and 4 and 500 light years away in different directions, glowing faintly in X-ray light, busy with the labor of making new stars. The ancient neutron stars left behind by some of those original explosions, Geminga, that nearby pulsar spinning steadily in the constellation Gemini, likely the remnant of one of the bombs, are still ticking. The iron is still falling in quantities so tiny as to be biologically meaningless but measurable. The bubble has not finished with its business, it has just slowed down. You live inside it. Right now. Wherever you are, whatever corner of this planet you are in, whatever time it is in your part of the night, the local bubble surrounds you. Above and below and in all directions, out to distances your mind genuinely cannot hold in its full scale, 1,000 light years. If you set out tonight at the speed of light, the fastest anything in the universe can travel, you would not reach the far wall of this cavity until the year 3025. Your great-great and many more great-grandchildren would have lived and died before the light you emitted tonight made it across the room we live in. And that room was dug by dying stars. There is something I keep returning to in thinking about all of this. Not the danger, but there is no meaningful danger from any of this. Not now, not for any time scale we can sensibly reason about. Not the drama, though the drama is real, and it is earned, but something quieter. Something about what it means to live in a place with this kind of history. The interstellar medium, the gas and dust between the stars, is not a passive backdrop. It is not the empty black of science textbook illustrations. It is a material, dynamic, structured thing carved by stellar winds and supernova blasts and the slow, gravitational collapse of molecular clouds shaped by millions of years of stellar life cycles, seeded with the chemistry of every explosion and every stellar wind that passed through it. And we are inside it, not observing it from a safe distance. Inside it. The interstellar medium is our medium. The local bubble is our immediate environment, our extended home. The cavity that gives our part of the galaxy its particular character. The iron in the ocean floor arrived here from a supernova blast that happened before our genus existed. The atoms in that iron were forged in the core of a star that completed its entire life cycle. Birth in a molecular cloud, main sequence hydrogen burning for millions of years, giant phase, core collapse, supernova, before the first creature you would recognize as vaguely ancestral to you ever walked upright. That iron crossed hundreds of light years of interstellar space. It arrived at the solar system. It was swept up, perhaps by the heliosphere's interaction with the interstellar medium, perhaps just by Earth's gravity pulling in what the interstellar medium offered as we passed through. It settled into the ocean. It lithified into rock. Human beings retrieved that rock from the seafloor and measured it in a laboratory and found the fingerprint of the explosion. That is not a small thing. That is the universe making itself legible, leaving evidence that can be found and read by the creatures it eventually produced. And the Antarctic snow, the fresh snow with its trace of iron-60 still arriving, still accumulating. Cole and colleagues detecting it in 2019. A ghost signal from explosions millions of years old still reaching us, still arriving like a letter posted by a civilization that has been extinct for longer than our lineage has existed. The postal service of the galaxy is slow, but it is thorough. The letter is still coming. Think about where you are right now. Maybe you are in bed, the room dim, some lamp still casting a warm light across the ceiling. Maybe you are on a train moving through a dark landscape, or on a couch with the sounds of the house settling around you. Wherever you are on the surface of a planet that is moving right now at roughly 20 kilometers per second around the Sun, and the solar system is moving at roughly 250 kilometers per second around the center of the Milky Way, and the whole solar system, you, the planet, the Sun, the heliosphere, the local fluff we are currently riding, is moving through the interior of the local bubble at some smaller relative velocity, slowly drifting the way a passenger on an ocean liner drifts through a room while the ship moves through the ocean. The bubble's walls are rushing outward at about 6.5 kilometers per second, not fast by stellar standards. A gentle, tired expansion, the last momentum of ancient violence bleeding off into the surrounding interstellar medium. On the walls, new stars are igniting. In Taurus, in Ophiuchus, in the other molecular clouds pinned to the shell, protostars are collapsing out of the swept-up material that the ancient supernovae compacted into those regions. They will live billions of years, some of them. They may have planetary systems. Some of those planets may, in the cosmically long, patient, statistically plausible way, develop their own complicated chemistry, their own long, slow evolutionary experiments. Those future stars, if they exist, were seeded in part by the same explosions that left iron in our ocean floor, the same stellar deaths that touched Earth's climate history, that rain faintly on Antarctic snow, that hollowed the cavity we live in. Those deaths are also, right now, causing births. The material swept up into the shell is compressing. Gravity is doing its patient work. Stars are forming. The local bubble is not only a tomb, it is also a womb, We started tonight in a very particular place. I asked where in the world you are, wherever you are listening from, and I want to come back to that now, because everything we have talked about, all of this, the 1,000-light-year cavity, the 15 ancient explosions, the radioactive iron in the Pacific, the fresh dust on Antarctic snow, the Ice Age timing, the heliosphere under pressure, the neutron stars still spinning in the dark. All of it is the context for the specific patch of space where your planet is, where you are. The local bubble is not far away. You are not looking at it from outside. You are not contemplating it through a telescope pointed at a distant region of the galaxy. You are inside it. You were born inside it. Every human who has ever lived has lived inside it. Every human civilization, every language, every poem, every war, every moment of love or grief or ordinary Tuesday afternoon, all of it happened inside the cavity blown by dying stars, inside the still warm, still slowly expanding evidence of ancient cataclysms. And the evidence of those cataclysms is in the rock beneath your oceans. The iron is there. It was put there by the universe, by physics, by the life cycle of stars that had no idea, obviously, that they were putting it there, that were simply doing what massive stars do when they run out of fuel, collapsing and exploding and sending their material outward in every direction, including the direction of a small, unremarkable solar system that would not arrive in the neighborhood for millions of years. There is no design in that, no intention, no cosmic housekeeping that cleared a comfortable space for us. The sun wandered in by coincidence. We are tenants who arrived after the demolition, moved into the ruins, and are only now beginning to understand the architecture of the building we live in. The 2022 paper by Zucker and Goodman and Alves gave us the clearest picture yet of that architecture. The shape of the walls, the distribution of the new star-forming regions on those walls, the history of the excavation in 3D. The work continues. Better maps will come. More precise measurements of the iron 60 pulses will come. The climate modeling will get better. The understanding will deepen. But even now, with what we know, it is enough. It is more than enough. The scale is true and the scale is staggering. The carving is real and the carvers left bodies. The touching of Earth by those stellar deaths, the iron, the isotopes, perhaps the climate, is documented in the rock and the ice and the ocean floor. You are sitting inside a hole in space 1,000 light-years wide and dying stars dug it. The iron they made is at the bottom of your oceans and in last year's Antarctic snow. The walls of the hole are where your galaxy is making new suns. The empty air of the hole is still 1,000,000 degrees, still glowing faintly in X-rays, still carrying the warmth of what burned here long ago. That is not a story about danger. That is not a story about doom. It is a story about where you actually are and what this place actually is and what it cost cosmically in stellar lives and released energy and millions of years of slow excavation to make the particular empty corner of the galaxy that you are, right now, riding through. You are a creature of the local bubble. You always have been, you just didn't know it had a name. Wherever you are listening from tonight, whatever time it is in your corner of the world, I hope that feels less like an abstraction now and more like a location, a specific, strange, beautiful, hard-won location, a blast crater that became a neighborhood, a void that contains, among other things, you. If you enjoyed this slow drift through the bubble, a gentle like and subscribe means more than you might think. Small creators like this one really do rely on your support to keep these quiet journeys going. And if you want to leave a trace of where you are in the world tonight, tell me in the comments. Where are you listening from? And what time is it there? I love knowing that these words find their way to so many different corners of the night. Sleep well. Carry the wonder with you into the dark. Close the books. Dim the lamp. Class is over, sleepy scholar.